Hi, welcome to Lecture 8 in the Introduction to Proof series. We're going to be going over section 2.1 from A General Introduction to the Art of Math today. The layout of our talk today is going to go something like this. We're going to give you some introductory material about logic. That's the main topic of the section. And then we'll talk about logical connectors and finally introduce Boolean algebra. So first, some introductory thing. First, a common feature in all areas of mathematics is that there are always undefined so-called atomic concepts that one needs to be aware of. This is the sort of issue that a person who might be trying to write a dictionary faces. Each time you try to define a word, you have to define it in terms of other words, presumably simpler words, but there's sort of a bottom to that, right? Eventually you have to find a word that everybody can just agree on, or a couple of words that we can all agree on, from which we can then define other things. That usually works just fine for people writing dictionaries because there are a bunch of sort of baby vocabulary words that we all agree on. We don't need the help of a dictionary. It's often amusing to try to read the dictionary entries for things like that because the truth is they're atomic concepts. So we have that in every branch of mathematics. There'll be terms that are just undefined, and we have to accept that the notion that different people have of what that concept is or what that word represents is more or less the same. It leads to some interesting features that sometimes, you can come up with new branches of mathematics just by having a reinterpretation of what a term is. That happened, for instance, in geometry. There's undefined terms in geometry, points and lines. I know what a point is. You know what a point is, I think. What's a line? Yeah, we get the idea. But in a branch of math called projective geometry, the points are actually lines. The points of the geometry are literally lines that go through the origin. So an example of perspective change, giving you a new kind of thing. Oh, I said that already. Points and lines and points on lines. Those are the undefined concepts in geometry. What's a point? In Euclid, the Greek translator says something like, a point is that which has no part. Which, I don't know. It sounds like mysticism to me. Lines are described as length without breadth. And the idea that a point can be on a line or that a line can go through a point reciprocally is called incidence. That's a little difficult to define too. So I said see Euclid. I wanted to actually show you a translation of the first book of Euclid that begins with definitions. And the first thing he has is what I said before. A point is that which has no part. A line is a breadthless length. Those make no sense. They really, I guess they make some level of sense. We sort of get an understanding for it, but they're not precise definitions. The ends of a line are points. Now I'm starting to buy that, but I guess we're talking about line segments in that case, if it's going to have ends. Suddenly in definition 4, he makes a difference between a line and a straight line. So apparently these lines back here in definition 2 were curvy things, or could have been anyway. Anyway, it goes on from there. It begins to the definitions begin to make more sense as you go later in them, but those first ones, you're suffering from the dictionary problem. How do you describe planes without being able to have lines? And lines are really undefinable terms. I hope I haven't beaten this thing to death here. If you go farther down in here, gosh, she has a lot of definitions in Euclid's beginning, but you get into some other things. Postulates, the ability to construct certain things. So if you have 2 points, you can draw a line in between them. They really do mean a line segment, I believe, in that case. And if you've got a line segment, you can continue it in a either direction, really. You can produce an infinite line from a well, they're all infinite, an infinitely long line from a segment. You can make circles. Postulate 4 is actually kind of an interesting one here. In Euclid, postulate 4 says that all right angles are equal to one another. And that actually is saying something a little more interesting than what it seems. It's sort of telling you that no matter where a right angle is in space, it's got the same measure. It's saying that that angle measure, and by extension, all angles, are invariant. If you move things around in space, it doesn't change the measure of the angles. And then there's postulate 5, which you notice is much longer in length. We'll definitely talk about postulate number 5 later. In Euclid, he also has these things he calls common notions. You may recognize the transitive property of equality, that when two things are equal to a third thing, they're equal to one another. If you add equals to equals, then the wholes are equal. That's describing a rule of algebra, right? It's okay to add the same thing on both sides of an equation. It's also okay to subtract the same thing from both sides of an equation. So anyway, these common notions and these postulates together, that's the axiom set that Euclid used for geometry. And every area of math that we're going to look at, there's going to be an axiom set. It's good advice to whatever branch of math you're trying to deal with, memorize the freaking axioms. Just get them in your head. Be able to spit them out instantly if you need them, because they're the keys to everything. All right, probably went on too long about Euclid there. So, yeah, in Euclid, we already saw this postulates. Now, I think my take on it is if you've got a sentence that involves the undefined terms, but you can't figure out any way to prove it, it doesn't seem to follow from other postulates that you've already accepted, then that means you've got to expand your list of postulates. If a thing can't be proved, but you believe it, you think it's true, or it should be true in the area of math you're working in, then make it a postulate. But don't go nuts on this. It's kind of bad form if you have 49 postulates. Keep it down to like Euclid level. There's like 10 of them there. That's reasonable. Okay. Yeah, he had 5 postulates, 5 common notions. Together, those are the axioms. All right, so we're about to talk about logic, and let's see all of this stuff in that milieu. The atomic concepts in logic are just these 3 things: the concept of true and false, and what is a sentence. And these are things that I think we can all agree on. We know what they mean, even though it's really hard to say what they mean. Could you define precisely what it means for a sentence to be true? You could probably say something philosophically like a true sentence is one that won't lead you to make mistakes. But now you've just substituted the mistakes for basically the word false. You just said a true sentence is one that isn't false. That's great, but then you're getting the same issue with trying to define false. Well, also, what is a sentence? Do I think I know what a sentence is? My shirt is blue. That's a sentence, right? Shirt my blue is, not so much. So there's got to be a syntax, a proper grammar to a sentence. It doesn't have to be perfect. You could talk like Yoda, right? The shirt blue is, and people would understand it. And so, yeah, I would accept that as a sentence. But if you totally scramble the words in most sentences, it becomes understandable. So we want something that parses properly in English or whatever language you're working in, and it makes some sense. But there's all kinds of sentences that seem okay and aren't. So we distinguish a new class. And this is making a definition of something that involves the primitive concepts, the atomic ideas. It involves the word sentence, and involves the words true, and involves the words false. It also has that and is and a. Those are just parts of speech, but more meaty issue is it has the word or in it. We don't really know what or is yet, but we're going to make or precise soon. So that's fine. So a sentence is something that's either true or false. In other words, you can figure out the truth value of a sentence. There's plenty of things that you can't figure out the truth value of. Ambiguity is a big issue. X is a prime number. Well, what the heck is X? Right? That's ambiguous. It's got a variable. I mean, you could say things about people, but if you don't specify well, then it's hard to say whether that sentence is true or false. John is a lawyer. I don't know who John is. It's an ambiguous sentence. John Edwards is a lawyer. Oh, I think he's on the Supreme Court. Cool. He's got to be a lawyer. So watch out for ambiguity. If it's there, there's actually reasonable ways to remove ambiguity. In fact, we'll see later, but this is what our quantifiers are all about. They create unambiguously true or false sentences out of things that previously were ambiguous. So ambiguity is an interesting concept, and it's one we can deal with. A much harder concept is the notion of undecidability. And this has far-reaching consequences. But Kurt Gödel, around the turn of the 20th century, I guess the early 1900s, proved that every single mathematical language that you can develop based on some small set of axioms. Now, he did require that the axioms be complicated enough that you could model the natural numbers in them. So sort of axioms with enough meat in them to produce an interesting theory. But every such logical language has undecidable propositions in it. What does it mean to be undecidable? Literally, that you can neither prove the thing, nor can you disprove it based off of your axioms. You can't tell. Might be true, might be false. The undecidable propositions have an interesting role to play. When you encounter an undecidable thing, you can make a choice. All right, we could add it into our axioms. Right? We could say, okay, this is going to be a new axiom then, and we'll get a whole new branch of a sort of a variant of the logical system or the mathematical system you were previously studying. That's kind of cool. And believe me, it happens more often than you might guess. Okay, so I don't want to actually discuss particular undecidable sentences. Let's take some baby steps before we start flying like that. So our next section is about the connections that we make between logical sentences. And but. That's going to be our first connector. And but, it turns out, mean the same thing. So here's a sentence somebody might say. They turned off my electricity, but I paid the bill. If somebody says that to you, you have to imagine, well, their electric is out. You know, if you go flip on the light switches, nothing happens. And also, you believe them that they paid the bill. So these two things, these separate thing about paying the bill and the electricity being off, they're both true. Isn't that what and means? If I say, I like ham and I like eggs, it means both of those things are true. So, but has the same meaning as and. I always find that strange. It's not as uncommon as you might think for languages to have words that have exactly the same denotation. They mean literally the same thing. And then in which case, why do they exist? Why do we have both an and a but? There's a connotation about it. The connotation with but is usually sort of surprise, that you're saying, okay, they turned off my electricity and I paid the bill, but doesn't sort of put out the amount of anger you're feeling at the electric company for turning you off even though you paid. Or is the other thing that we'll see as a connector, and we could use or to create a compound sentence. Close the door or bugs will get in the house. Sure, right? So there's two sentences there. There's two separate little atomic parts. Close the door and bugs will get in the house. When we stick the or in between them, it means, well, we'll see what it means. I think you know what it means, right? These two ways of connecting sentences are called conjunction and disjunction in math. In English, class, they'll have used the word conjunction. Conjunction is any word that's used to hook phrases together into a more complicated sentence. I heartily recommend the Schoolhouse Rock video, Conjunction Junction, because it's fun. It's silly, but fun. But conjunction means something very specific when we're talking about logic. It's the and operator, the hooking together of two clauses with an and. And we use disjunction for the other case where we use or. Now, we're going to see some of the sort of brevity that math can introduce into our language or into our use. It makes math so succinct. We'll end up using variables to stand for entire sentences. In fact, entire statements. I want these things to be the sort that are either true or false. I don't know if that's a typo or just a little bit weak use of language here, because I probably should say statements, because I do mean the good kind that are either true or false. But of course, those are sentences, so I haven't lied here. Okay, so an example. P is the sentence, the electricity has been shut off, and Q is the sentence, the electric bill was paid. Right. So here's some symbols we'll use to do the hooking together. And it's like a less than sign or a greater than sign, but it's pointing upwards. And the other one is it looks like the letter V. Right? Use those to hook predicates together to make more complicated compound sentences. Predicates is essentially a synonym for statements, right? These are the things like the electricity has been shut off and the electric bill was paid. So let's be really explicit about this. The upward arrow looking thing is conjunction. It's the thing that looks like that is and, the and operation. I always point out that it looks a lot like a capital letter A, doesn't it? Except it's missing the little bar. So the thing that looks like an A, it goes with and then the other one's the other one. The other one is disjunction, or the or operator. So this is a little tough. The thing I've written right there, P and Q, is the same thing exactly as this whole long sentence. They turned off my electricity, but I paid the bill. Right? So you see the compactification that's occurred when we do things like that. All right, truth tables. This is going to be sort of a great tool for expanding our lexicon of things we know about. So to introduce this, I'll just point out, if you've got two things, a sentence on either side of your connector, and each of those is either true or false, there's a total of 4 possibilities. They could, let's see, both be true, one be false and the other true, vice versa, or both false, right? So you could get I don't know, it's like flipping 2 coins. You could have 2 heads, 2 tails, a head and a tail, or a tail and a head. The 4 possibilities, what are they? Yeah, just a convention that is carried out in JIAM and that I'm going to stick with in these lectures. Commonly people use T and F for true and false, and unfortunately, if your handwriting stinks as much as mine does, F's easily end up looking like T's or vice versa. So I'm switching to using the Greek letter phi for false, and T sticks with true, or true sticks with T. I don't know how to say that. Anyway, phi is actually the F in the Greek alphabet, or actually the symbol looks just like it in the Cyrillic alphabet. So it sort of makes sense that we use that for F. And anyway, it's definitely a different looking symbol than T is, so you won't get them confused. So here is a truth table illustrating all the possible outcomes for 2 sentences. One sentence is the sun is shining. The second sentence is it is raining. The first line of this table has both of those true. Of course, that never happens, right? Has anybody ever seen a sun shower? Yeah, it actually does happen. It's rare, but you can have the sun out and rain coming out of the sky. The sun is shining and it's not raining all the time. That happens, unless you live in Oregon. I shouldn't diss Oregon. I have a good friend who's from Oregon, but he left there because it rained so much. No, not entirely. Anyway, the sun is not shining, false for the sun is shining, and it is raining. That makes sense, right? It's cloudy, but then it's raining. It usually rains when it's cloudy. And the last one is it's neither sunshine nor rain, just a gray day, right? That happens too. So all four of those possibilities can happen, and I guess I would like you to think of those as alternate realities. You can put yourself in, you can imagine in your mind's eye at least being in a world where it is shining, the sun is shining, and it is raining. But any one of these other four is a possibility too. So, all right. So let's actually use a truth table. I'm going to build my own truth table here. Let's bring this up to the fore and remove the calculator. You can see me writing. I want to build a truth table for conjunction. So it's going to look like this. I use P and Q. In the textbook, they usually use A and B. But P and Q are actually more commonly used in logic texts. So I don't know why. I think it might go back to like ancient Greece or something. They used P and Q there. So we're going to make all four possible combinations of true and false for P and Q. But I want a third column here, and that's going to contain the logical true or false value of the conjunction. That's the one that looks like an A, P and Q. All right, so the reason I want to do this by hand rather than just showing one to you is I think it's good to get used to sort of seeing the process by which you fill out the truth tables. There's a flow to it that you want to kind of internalize. And the flow is something like this. Start with everybody true. Then take the rightmost guy and just have it alternate. So it'll go true, then false, true, then false. Okay. The next guy is going to alternate too, but in groups. So it's going to have a group of two trues, and then it's going to have a group of true falses. I think I just said true falses. I meant two falses. So two T's, two F's, a T and F, a T and F. And that's a nice way to ensure that you got all four possibilities here. Not so hard to do when there's only four, but when there's four variables, for instance, you'd have 16 rows to fill out like this. So it's nice to have a systematic way to ensure that you hit all the possible combinations of the true and false. So what do you think is the value of P and Q when P and Q are both true? Of course, that's going to be true. And you probably know this. If even one of the statements is false, then the and is going to be false. So we get a single true, and then it's F, 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 or phi, phi, phi. So there you go. That's effectively defining what it means to form the conjunction of two sentences, of two statements. The conjunction is a new sentence that has this property. It's true when both of the input sentences are true, and it's false in every other scenario. What's next? Oh, of course, disjunction. And now I've lost the camera. Oh, and I'm going to keep losing it if I do that. All right, let me get it back to the middle here. All right, so let's make a truth table for the disjunction. I know this may seem boring, but I want to actually construct the truth table again because repetition, it helps you remember things. So we have P and Q. Remember, you begin with the double T's up top and alternate Q, true, false, and then batches of two trues and then two falses. All right, and the other column we want here is the disjunction of P and Q. So P or Q. So you read that. So when is P or Q true? There is slight disagreement about this. If the first one's true and the second one's true, we definitely think of them as true. And when it's false true, the vice versa rule, we definitely think of it as true. And in the bottom row there, where P is false and Q is false, the or is definitely false. Everybody likes that. The one that's contentious is the top row. What do you do with an or sentence when P is true and Q is true? People are used to thinking of or as expressing alternatives. You want to go to Miami for your vacation, or maybe go to Canada. It's one or the other. You can't do them both. Right? So that feels like this would be a false. But in logic, this is almost always represented as a T. There's actually another thing called XOR, which would have an F in that position, but it really doesn't get used that much in the logic world. So for logicians, or is defined like this. If either one of the sentences is true, including if both of them are true, you get true in the or. And it's only false in one scenario, if both inputs are false. All right. Whoops, I guess I should put this back because there's one more thing we need to do a truth table for. This is an easy one though, so it won't take this long. The idea of negation. So this is different from conjunction and disjunction, which were things that were infixed notation, right? They were actually the sort of things we saw in the section on relations. They go in between two inputs. Negation is a unary operator. It goes in front of an input, and it looks like, and it acts rather like a minus sign. So the difference is slight. A lot of times people use this symbol, and this is what is used in the primary version of JIAM. It's like a minus sign, but with a little hook on the end. I feel like I've made the hook a bit on the long side, so this part here is supposed to be kind of smallish. Some people do not care for that symbol. An alternative you may see a lot is a sort of a tilde, little squiggle thing, so not P, like that. And I just said it, not P. This is the idea of giving exactly the opposite truth value that P did. So if in this truth table, it's kind of a small, silly one, there's only a single variable, P, and P is either true or it's false. And not P is false when P is true, and it's true when P is false. So you get this, it's like a thing that switches in the truthiness of the thing to the other. All right, so that's negation. These three things together let you build a lot of stuff. You can do some impressive things with just and, or, and not. Let's put this to the side. All right, so yeah, the impressive thing that you can do with those two connectors and that one unary operator is build an entire new kind of algebra. I didn't give the name in the slides, but this is known as Boolean algebra. And there was a man named George Boole who essentially started this subject, and so it's in honor of him. Boole. Oh, I did write the words Boolean algebra at the title of the slide. It's Boolean algebra. So I want to remind you a little bit about how the operators in ordinary algebra work. There's precedence amongst them, and people often use this acronym PEMDAS to remember that precedence. Some people say, "Please excuse my dear Aunt Sally," as a way to remember that, which I feel like just saying PEMDAS is enough, but whatever. I'll also point out that if you're on a graphing calculator, or one of these TI ones at least, you'll see the symbols occurring in the PEMDAS order on the keyboard. Here's your parentheses, and then there's your exponent, times and divides are next, and then minus and plus are after that. So it's got a little bump in it, but basically go across and then down the thing. That's the order of precedence. What does that really mean? Well, it means that if you have an expression where you can't tell what order the person wanted, do anything in parentheses first. If they put the parentheses in, they meant do that stuff on the inside of the parentheses before anything else. Next most important is exponents. If you see a power, raise that power before you do any multiplying or dividing. And finally, do any multiplying or dividing before you do any adding or subtracting. People rarely mention that M and D are at the same level of importance. So does it matter if you multiply first and then divide, or you do the division first and then multiply? Turns out it actually doesn't. The same thing is true of adding and subtracting. So we don't have to be terribly concerned about mixing up the groups, but the additive things, the multiplicative things, and the exponent things, those need to be kept separate. I have a colleague who wishes that this acronym was GEMDAS with a G in front because of a good reason. There's other things besides parentheses that serve to group. For instance, the square root sign has a grouping feature. A long fraction bar, everything in the numerator and everything in the denominator are grouped by that long bar. So it might, well, the tradition now is PEMDAS, but really think of the parentheses as including grouping symbols like fraction bars and whatnot. So why do these precedences of the operations happen the way they do? Well, it's basically because multiplication is repeated addition. And we saw in the section on algorithms, division is repeated subtraction. So it makes sense that multiplying happens before adding because multiplying is built on adding. It's more important. It's like you do a bunch of adds and that's multiplying. And exponentiation, well, that's repeated multiplication, isn't it? So powers are a more important thing than multiplying. So it makes sense again that we have E coming before M in the PEMDAS acronym. Okay, here's an issue we got to face. The logical connectors and or, they have nothing to do with one another. You can't say that and is repeated oring or vice versa. And in truth, they don't have a predefined precedence. We don't say one is better than the other. There's a common version of the notation for logic that especially is done in computer science programs where they use the dot, like the multiplication dot for and they use a plus sign for or. And I actually prefer that we use these symbols, the up caret and the down caret, because when you use dot and plus, you're sort of you have this ingrained tendency to think that the dots happen first and the pluses happen second. And that isn't necessarily the case. And it also looks pretty funky when you've got parentheses that that tell you to add before you should multiply. Anyway, so what's the lesson from that? Oh, wait, there's one other thing, logical negation. That is got a little bit better precedence. The negation symbol binds a little more tightly than and or. So if you saw something like, let me do this just on the screen here. If I saw not P and Q, that really means do the not to P first and then end it with Q. Right? The parentheses I just put in were for effect. You don't need them because the not sign binds to the P before, it happens first before you do the and. So what's the takeaway? Use parentheses to make sure that what you're writing is what you actually mean. You don't have to be redundant, so don't go crazy on putting parentheses in that aren't needed, but do use them. Don't be cheap about parentheses. So here's an example. I've got the sentence A and B or C there. What does it mean? it's actually got two different possibilities, A and B, ANDed together, and then ORed with C. That's one way you could interpret this. I guess if you thought about reading left to right as a standard way to group, then you would probably mean this one. I, I've never used that convention in Boolean algebra. Perhaps some people do, but I just insist on parentheses. We could also have this thought of as A ANDed with the result of doing B or C. And, and these two different ways of interpreting it have different meanings. They literally have different truth tables if you like. In fact, you know what? Let's do that. We should see the truth table of both of these. I'm going to be a little economical here and put both truth tables on the same table, but mostly just so that it'll allow us to compare things a little bit more easily. All right, so how's this truth table going to look? Now we've got a situation where there are three variables, three things that can independently of one another be true or false. So two choices for the first one, two choices for the second one, two choices for the third one. That means 8 total options. Let's see why my systematic way of filling out a truth table is of some use here. All right, so I'm going to need columns for A, B, and C. I'm worried that my paper is not quite wide enough for this. I carefully made these small sheets of paper for the display, but I think I'll run one sideways here so we can just make it on the screen. Okay, A, B, and C. And then we have first A ANDed with B, and then ORed with C. That's parentheses around the first group. And secondly, this one's going to go off the edge, unfortunately, but we'll remember what it is. A ANDed with the result of B or C. So that's the column headings for my truth table. I'm just going to put dividers between the parts. All right, so the truth table starts off with everybody true in the top row. And then we're going to let C alternate back and forth, true and false. So true, false, true, false, true, false. And I said before there should be 8 rows to this table, so I'm just going off the bottom of the screen too. There's 8 of them. Now, just like we did before, I'm going to have B, again, alternate, but alternate in groups of 2. So 2 trues and 2 falses. Then 2 trues, and then 2 falses. Now you might notice something. There's a kind of a vertical division. The upper half of the table and the bottom half of the table are exactly the same so far. And this is where the first variable, A, is going to come into place. In the top half of the table, all of those are going to be true because we're going to alternate now in groups of 4. So we'll have 4 T's, and then we'll have 4 F's. All right, now this next thing is supposed to be the result of doing A and B first, and then ORing it with C. And there is a common way people sort of cheat on truth tables, which is to write in, maybe pencil in an intermediate result right in the midst of the column. So I'm going to do this in blue pen so that we don't see it. But right under this AND symbol, so not under A or B, but under the AND, I'm going to excuse me, I'm going to put in the result of doing A and B. And it's going to be true in just the top 2 rows of the table. Because everywhere else from there on down, at least one of the things is false. So we got 2 trues, and false, 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 and false. Oh, I just remembered I can adjust this and then we can see a little bit more of it. Silly of me. Okay. Now, when I OR that with C, that has an interesting effect. Anything that where A and B is true will be true, but in addition to that, anything where C is true will be true. So the final thing, that this is not penciled in anymore, this is the real answer, is, well, it'll certainly be true in these top two positions because we've got a T on the left of the OR, but it'll also be true in the third position, the third row, because there's a T, the C value is T on the right of the OR sign. Here it'll be false because both C and the A and B part are false. And where else is it going to be true? You can probably see them. They're down here and here. That's row 5 and row 7. So true, false, true, false. Yep. Let's play that same thing with the A and B or C. I don't know, does my voice actually somewhat convey the grouping when I say A and B or C? That's the idea. So we want to first sort of pencil in what's the result of doing B or C. Remember, B, the OR connector is true when any of the stuff is true. So it's actually usually smart for the OR connector to just look for where is it false. That'll be the small number of things, and then fill everything else in with T's. And this OR connector is false in row 4, where B and C are both false. And it's also false in row 8, where they're both false. And so it's true in the remaining positions. 3 T's in both the upper block and the lower block. Okay. Now we're going to AND that with A. Well, look at what A's deal was. It was only true in the top. We're going to AND something with something that's true in the top but false in the bottom. What's going to happen to the bottom? It's all false. So we get 4 falses down here. Those little T's that we penciled in, they don't matter. The fact that we're using the AND connector and the fact that A is false on one side of that AND connector just overwhelms that other thing. In the top half, though, really the A being true, the AND connector does nothing. We just get the T values that are written in blue. So it's 3 T's, just like these 3 blue T's, and then an F, and then F's all the way down. So are these things the same? Well, this actually raises a point that's of some importance. What does it mean for them to be the same? What does it mean for two logical things constructed out of the predicate variables and these connectors to be the same? Well, I take it to mean they have exactly the same truth tables. That is, the pattern of T's and F's you're seeing should be the same, and they're not. In one alternate universe right here, one's true and the other's false. And in another one right here, one's true and the other's false. They agree in a lot of positions, but not every position. So you can't say they have identical truth content. Okay, so that's a pretty discursive take on A and B or C. All right, so we're going to now look at, well, something that we can use as a tool to help visualize logic to a certain extent, but also I think it's a useful topic to see why logic circuits have, why logical connectors have some of the rules that they do. In the textbook, they talk about transistors, and it shows the series and parallel connection of transistors. I'm going to say this with just switches. So switches are maybe a little bit easier to understand. Transistors aren't all that bad, but you can think of a transistor as just being a switch that's controlled by electricity. So a switch really has the right idea to it. In an electrical circuit diagram, we draw switches like that. So you have 2 dots, wire coming up to the one dot, wire going away from the other dot, and then there's this, well, it's really meant to express sort of a bit of wire that's at an angle, but if you pushed on it, it would come down and touch this other one, and then, pardon me, electricity could flow. So that's a way you draw a switch on an electrical diagram. there are multiple kinds of switch, but this is the easiest type of switch to draw anyway. So series connection means this. You put two switches, one after the other, in a bit of wire. So we'll have two of these places where there's dots with the little leaf spring looking things there. Now, really an electrical circuit needs to be literally a circuit. There has to be a source of energy, a battery or something, and then the wire has to eventually lead back to that source. So the batteries in an electrical diagram are often drawn like that, alternating short and long lines. And so electricity would go through these, go out of the battery, go through these switches. If they were closed, it would go through them, and then it will eventually come back to the battery. That's called completing the circuit. If I just did this, if I just let the wire come back, that's actually called a short circuit, because once these switches get pushed, there's nothing but wire between the two ends of the battery. And if you do that, the wire gets hot and the battery may explode. So don't do that. If you're building circuits, don't make short circuits. That's how you get the smoke to come out of electrical things. If, on the other hand, something in the circuit can dissipate the energy, I'm going to try to draw a sort of a fake light bulb here. Now it'll be fine. That light bulb will dissipate some of the power, and we won't have a totally short circuit. This might still get warm depending on the wattage of the light bulb, but it's not going to cause a fire. All right, so that's a lot of talk about circuitry, but I really want to talk about the logic. What's the logic of pushing these switches? If I push the one on the left, does the light bulb come on? I got to push them both to make the light bulb come on. So that actually is the implementation of AND. You got to push switch A and switch B to make the light bulb come on. I'd almost like to build a little device like this and have it hidden away, and you'd push the things and eventually figure out that if when you were holding both of them down, the light bulb came on, and you'd go, what's inside of there? And then you'd open it up and see. It might be a fun toy for budding electrical engineers when they're little kids. All right, so that is AND. We've got the implementation of AND right there. How could we make an arrangement of switches so that the light bulb would come on with either one of them on? That's what's known as a parallel circuit. And let me try to draw a parallel circuit for you here. Battery comes in, juice comes out of the battery, then the wire splits. And it goes to two different switches that are in different branches, is actually how electricians refer to these. And then the wires come back together and continue on their merry way to do something. Maybe, again, they go into a light bulb. And finally, the juice comes back and we complete the circuit at the other end of the battery. Let's put a glass envelope around our bulb. So yeah, can you see how this is going to work? If I push the top switch, the light bulb comes on. If I push the bottom switch, the light bulb comes on. What if I push both switches? The light bulb comes on brighter, maybe? I don't know, it's just on again. So that's why this parallel circuit implementing OR, which I should probably write on here, this is probably the reason why we use the inclusive sense of OR in logic. No, it's probably not, but it's certainly illustrative of it. It's easier to make computer circuitry that implements the inclusive sense of OR than it is to make the exclusive sense. Okay, so we've done those two things. We made series connections to implement AND, parallel connections to implement OR, and I just spoke to you about why we use the non-exclusive OR in math. Now, there are symbols, and they're now on the screen in front of you, for these things all at once. So this kind of thing that requires both inputs to be selected or turned on, or a voltage applied to both before it makes the thing light up, that's the AND gate. It is well, it's the thing over here on the left. It looks rather like a capital letter D, doesn't it? So I think this is kind of nice for and. The symbol for and looks like the letter A, and the symbol for the and gate looks like the letter D. I think I'm mirror imaged for you guys, but is that a D? Oh well. Yeah, so that gate is something where the output of it gets energized, voltage appears on it, if both of the inputs on it are energized. Now, the kinds of diagrams where logic elements like these are used usually don't bother with what I was doing here, where the electricity comes back to the circuit to complete the circuit, because the engineers that are working with this kind of stuff know that happens. They're already good with that. So typically, what you would draw is a voltage source, and it's connected to something called ground, which is drawn with decreasing size things. And when it goes off and does other junk, eventually that can be connected to ground as well. And this is where the voltage gets back. There actually are were homes in ancient days with the beginnings of electricity where they literally used the ground as the return, so that yeah, voltage would go through and run toasters and stuff, and then the other end of the circuit was just attached to a spike hammered into the ground. Um, it leads to interesting troubleshooting issues sometimes when you have a thing like that. Most houses today are grounded, but that's for a different reason. The ground isn't used as a way to be the return path for the electricity. It's there to help with lightning protection and really safety. It helps people from being shocked. But that's neither here nor there. What we've got in the slide here is the and symbol. So I'm gonna draw them by hand as well, so I can talk about them. I just gave you this bit that the one that looks like a capital letter D is and I'm going to write it with the capital letter D on the end just to help remind us. I don't know if this helps, but I like the or symbol. I'd like to notice that the or symbol has a point on the end of it, whereas the and symbol doesn't. It's curvy, right? And the letter R in or has a point on the. I don't know. Maybe that's weak. Maybe you just remember the one that looks like a D is and the other one is or. But it is supposed to be curvy on the back, curvy on both other sides, and reach a point, not be kind of flat nosed the way the and operator is. Just pointing that stuff out. The not element in a circuit is called a negator, and it looks like it's drawn there. So it's really just the little circle on the end that is used to do negation. So it's just stuck on this little triangle to indicate like a circle has got to be put on something. But the circle is the thing that actually is used to indicate negation for uh, electrical engineers. And so that leads to things that look like this, an AND gate with a circle right there. So that's the negation of an AND. It's called NAND. And the negation of OR would look like this. I'm sorry, the lines went past because I was going fast, but this is the NOR operator, the negation of OR. Those two connectors get discussed in the homework in JIAM in section 2.1. So you don't need these. And for the rest of the textbook and certainly in the section about logic circuits as we're doing it, you don't need them. I just thought might as well show you that's something that you may encounter in a future life. Yep, okay. You can use these circuit diagrams, by the way, to help us understand something about the laws of Boolean logic. I'll mention three of the laws here, but I'm really only going to use circuit diagrams to show you two of them. One of them is just this: if you run two inputs into an AND gate, or if you suppose that was A and B, then the output is A and B. What if you just ran them in the other order? So you took A and B, and you switched them around, and then let them go into the AND gate. What is the meaning of that? It doesn't change anything. The output has to have both of them on in order to become on, so it's still A and B. But this thing is really B and A, isn't it? So it's telling you that commutation works. You can, because the wires could be easily switched without having any effect on the output. The symbols could be switched in an algebraic expression. That one's easy. The associative law, which leads to a shorthand that we're going to look at, is not quite as easy. What does the associative law say? Do you remember this from regular algebra? If you have the same operation, like multiplication, you can write that and it's unambiguous. That is, you could think of that as A times B times C, or you could say, group the second two things first. These are the same because everything's multiplying. Nothing to worry about. So if you have the same connector and it's a Boolean type, you can do the same. The parentheses are sort of extraneous, although I usually recommend people to put them in anyway. If the operators are all the same, it's fine. So the associative law for AND would look like this. A ANDed with B, parens ANDed with C, is the same thing as A ANDed with B and C, with parens around the second group. What does that look like in logic diagrams? I'm going to have A, B, and C be these three wires. The first one says hook A and B together into an AND gate, and then bring that together with the C input line into another AND gate, and then that's your output. And the second one says, well, let's do it again, A, B, C. You want B and C to go into that first AND gate, then that output together with A into another AND gate, and that's your output. And since these are the same, here's the shorthand that people use. You can just sort of think of a massive AND of a bunch of junk. Right? So you can replace that with a 3-input AND gate, a kind of a giant AND that has 3 wires leading into it. That's just graphical shorthand. It really, if you were trying to build a circuit that did this, you'd have to think of it this one or the other of these ways, and then look inside of those objects and put the actual transistors in. But we can definitely think of an AND gate with multiple inputs, and it makes sense because of the associative law. The distributive law I don't want to talk about right now, but we will look at that in section, 2.3. So it's coming. Okay, so there's a concept that's going to be very useful for us in designing circuits that have particular outputs, but this also means coming up with Boolean expressions that have specified true-false patterns. There's the same idea. The concept is called a recognizer, and it comes from thinking about this sort of multi-input circuit. If the input lines are A, B, and C, what does this guy do? Let me. It's going to be horrible, but let me go ahead and make the truth table for this. A, B, C. We'll say our output here. I guess I'm going to use true and false for the output, even though it would probably be 5 volts and 0 volts if it was real logic. But let's see. Everybody starts with trues across the top row, and then we got alternation in the C row, C column, excuse me. True, false, true, false. This is the midline. True, false, true, false. Okay. Then this guy is in groups of 2 trues, 2 falses, 2 trues, 2 falses. And the A guy is 4 trues, followed by 4 falses. I hope you're I hope some of you at least are thinking, why is he bothering with this? Because this is going to be a trivial result, isn't it? If you haven't thought that yet, think about it now. When is the and of these three variables actually going to be positive or true? Just there. Just there. Everywhere else, it's false. So what that multi-input AND gate does is it recognizes row one. It recognizes the state TTT on the inputs A, B, and C. If I wanted to recognize other rows, I can do that by just strategically inserting negators or not gates into the inputs before they run into that AND. Let me give an example. I'll try to put it down low. Suppose I had a not gate on the A line, left the B line okay, and then put a not on the C too. Why not? Okay, so these are input lines A, B, and C. And now we feed that into one of these triple input AND gates. In what row of the table does that turn on? Because of the nots, it happens when A is not on, when A is false, when B is on, and when C is not on. That is false, true, false. Where is false, true, false? That's right here. So the circuit I just created, this guy, would have a true in that position and falses everywhere else. Maybe I don't need to draw them all. You get the idea, right? Dot, 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 dot. It recognizes exactly one row of the truth table. Now, why am I showing you this? Well, the idea of a recognizer lets you build a circuit, and the concept behind that circuit actually leads to a thing in logic called disjunctive normal form. Disjunctive normal form is basically saying first you do this, or on the outside you have a disjunction, an or, and on the inside you have the other thing, conjunction. So disjunctive normal form is the or of a bunch of ands. The ands will be recognizers like this, and we'll or them together to make a specified I/O table for a circuit or output table for a logical expression. So, all right, we're going to look at an example of this in the book. It's not there, sorry. Section 2.5. Oh, I'm ahead of myself here. There it is. Figure 2.5. So this is a circuit. Do you see that it is, an and up here, a giant three input and, an and down here, and an and at the very bottom. The ands have some things, some of their lines negated and others not. The one at the bottom has them all left alone. The inputs, in this case I used X, Y, and Z, the inputs are also kind of distributed in a nice way. This is what in computer architecture might be called a bus. I'm leading the X wire all the way down the page so that I can use it in different places. The Y wire all the way down the page, again, used in different places. But I've kept the same convention that in each of these AND gates, the X, the Y, and the Z inputs occur in that order. So this is just sort of plumbing to make the X, Y, and Z things all come up to the corresponding recognizers, because that's what these are. What does the top AND gate recognize? That's when X is false and Y and Z are true. If you were doing logic circuits, you'd actually call that 0, 1, 1. But let's call it false, true, true for our purposes now. The second logic circuit recognizes true, true, false. And the last one recognizes true, true, true. Now, I better have the table in here. No, I don't. Oh, but I have the logical expression written down. This is it. The negation of X ANDed with Y ANDed with Z, all in parens, ORed with, okay, this is X, Y, and the negation of Z. That's the middle guy. And that's ORed with an addition X and Y and Z with no knots on anybody. That's the bottom thing. I almost feel like it's not worth our time, so I'm not going to build a full version of this thing, but I could, on at least on this thing, I'll use a different color, indicate what the output table would be like. So the states that were recognized are true, true, true. That's the top. Then what was the top one of these circuits? That's false, true, true. That's here. And then the middle guy is true, true, false. That's here. So the circuit that we've got there and the Boolean expression that was just under it would produce this output. True, true, false, false, true, false, false, false. More often, though, we would have the opposite job to do. Somebody would say, we need to have a circuit that builds this particular pattern of ins and outs, or patterns of trues and falses in these different scenarios. Design the circuit. Disjunctive normal form does it for you. Boom, you've got an instance. Now, it is not always the most efficient way. In fact, it's usually the least efficient way to do it. And in modern computer architecture, they are working hard to eliminate, as many transistors as they can. So the fewer number of transistors they use to build a particular circuit, the better. So they put quite a deal of effort into simplifying circuits, but it's nice to have somewhere to start with. So you could use something like disjunctive normal form to get an initial pass at it, and then try different things to make it simpler. Oh, wrong thing. I'll return to the slides. We did that figure. Great. We are at the end of today's slides, so that's a wrap. Thanks for paying attention, and have a great rest of your day.